Well, guys, I hope you looked at the videos or read the notes, or in fact did everything, as this material can be very hard. And of course, if you have any questions at the end of the class, don't hesitate to ask me questions, right? I try to stay as long as I possibly can, and I can definitely stay for at least 1 hour, which is your office hours, okay? Now, it also helps me to see who participates, and how you participate. And this way, if your video is on, I might be able to have a chance to see your eyes and know maybe if you understood it or not without you asking for it, okay? And also, I would like to be familiar with you, so I know who am I talking to. Okay, guys, so do you remember where you go? For this course, just to make sure everybody remembers, you go to Stat 311 Probability Theory, you click on it. And everything I have to tell you is here. So probability lecture notes is what I read from. Good? And we are in combinatorial analysis, and we have covered all the way to the binomial theorem, which, just for the purpose of this class, I will repeat a few ideas there. Good, James. You got Master Margarita. You show me afterwards maybe which translation you have gotten. That's, by the way, guys, as it would be nice, and that's of course if you have time. I definitely like this book, and I tried it on a few people. Some people really love the translation. I think at least I have one person that loved the English translation. And this is called, and okay. So if you want to try this book in Russian, it's very, very good book. In English, I have never read it. So, but one of my favorite, I'm reading it probably for the 5th time because it's that good. So back to the lesson. Yeah, if you don't understand why I started talking about it, somebody messaged me of my students and said that they have ordered this book and now it arrived. So I just remember, okay, good. You perhaps would like to do the same. All right, so here is what we talked about multiplication, guys. When we multiply two parentheses one against another, it ends up happening that we have every combination from a member of first parenthesis with a member of second parenthesis. And therefore, you can see that since we have one combination in here, or two possibilities here, and 3 possibilities here, altogether it's 2 times 3 or 6 possibilities. Good? Now, if you have 3 parentheses, each box here represents a contribution from one parenthesis. This parenthesis is capable of contributing 2 elements, this is capable of contributing 3, and this is capable of contributing 4. So it's 2 times 3 times 4, or 12 possibilities. That leads to the ability to figure out how to expand x plus y to any integer power. So obviously, how to expand x plus 1 to the first power, you don't need to do anything. To the square power, look at it, it's 2 parentheses where we can label this red index is parenthesis 1, the blue index is parenthesis 2, okay? So here goes a contribution from parenthesis 1, either x or y, and here goes contribution from parenthesis 2. When we don't simplify, we then have 2 times 2 or 2 squared, 4 possibilities, which if we group together, guys, we can group based on the number of copies of x attained. So when I have a y squared, that means I have 0 x's, which means first parenthesis had to contribute a y and second parenthesis has also to contribute a y. There is only one way to do that, okay? Then the instance when we have 1x, if we have only 1x, that means that 1x either came from this box or from that box. So there are 2 possibilities. That's why we have the 2 here. You see? Because either this is x and this is y, or this is y and this is x, and I indicated it here, okay? Everyone is clear, guys? So maybe if I were to write the notes today, I would have written this as my blue parenthesis and written this as x plus y, the blue x plus the blue y. Good? And I would have written the other parentheses as the red parenthesis where it has the red x and the red y. Now, if I obtain the situation where I have x, y, right? How could I obtain the x, y? Well, only two possibilities. Either I had x from the first parenthesis or I had y from the first parenthesis. Yes? Those are the two possibilities. And that means if I had x from the first parenthesis, the second parenthesis had to contribute a y, or in this case, second parenthesis had to contribute an x. You see why we have the index 2? In the expansion, we have red x, blue y, or red y, blue x. Two possibilities. Good? And that's how we collapse it. You see why we can collapse it, right? You can actually let's just make a small comprehension check, guys. Very small comprehension check, and please participate, all of you, and participate fast. I don't have time. Suppose that I expanded x plus y to the power of 7. Okay. So first question I want to know is how many summons. You understand what is a summon? Summon is a piece that you're adding without simplification. Tell me, please, right away, how many summons without simplification. Don't simplify the number naturally. Okay, Erin, wonderful. And the rest of you, it should be immediate, if you understood the idea. 2 to the 7, guys. I hope it's not because you took the lead of Erin when she wrote it, but you all see that it's 2 to the 7. Yes? It's 2 to the 7. Okay, second question. How many summons when simplified?
Hello, Arkady.
Hello, Fiona.
Yes. Can I ask you a question?
Yes.
Why is it 2 to the 7 for the first one?
Of course. So it's 2 to the 7 for the first case because we can run out of colors, but really this expression can be thought of as x plus y times x plus y, right, all the way to x plus y. Now this is parenthesis 1, parenthesis 2, all the way to parenthesis 7. Yes. Now you can imagine the parentheses as being given destiny. So the destiny is either to produce an x or to produce a y. Okay. So when we multiply, look at it. When I multiply it through two parentheses, it's either x times x or x times y. You see. So when you think about it, it's always one term, either x from the parentheses or y from the parentheses. So each summand before I simplify has 7 pieces. So this is from parenthesis 1, from parenthesis 2, from parenthesis 3, all the way to parenthesis 7. Okay. So what goes in this box? Either x or y. There are two possibilities. So there are two possibilities. This box has two possibilities. This box has two possibilities, and this has two possibilities. So it's by principle of counting, by the generalized principle of counting. 2 multiplied by 2 multiplied by 2. You do the multiplication 7 times because you have 7 boxes. Okay.
Right.
So just to show you quickly, if it's x plus y squared, this is x plus y times x plus
X
y.
plus y, right.
Right. So you can see the boxes. You can see that the possibilities are x. This is from first parenthesis and second parenthesis. So you have x times x plus x times y plus x
X.
So plus y times x.
Right.
Okay. Plus
And then
y
y
times
squared.
x and y. Yes. So this
Yeah,
means
yeah.
this is the first box. This is from first box. This is and this is second box. This is first, second. This is first, second, and first, second. You see where you have the fourth? So this has
Yeah.
two possibilities. You can see here it's either x or there is y. The second has two possibilities, either x or y. So that's what happens there. Okay.
Okay.
I hope that helps, guys. And if it doesn't, if it's too quick, you do stay with me after class. And if you do, I will explain it slower. Right. So guys, next question was how many summons when simplified? I don't ask you what they look like, but how many terms will I be added when I simplified everything to the greatest extent possible? So Sarah says 21. No. Think again. Okay. What I mean, you understand how many terms between which you see additions? That's what I'm asking. Okay. Exactly. Exactly, Alan, it would be n plus 1 in general, or 8 in this case. I hope you all see that the answer is 8. Now, why is the answer 8, guys? The answer is 8 because look at it. I group based on how many x's I have, right? When I multiply, I have x, y, right? And how many x's do I have? So I either have 0 x's or I have 1x or 2x's or 3x's. I can just count by the x's all the way to 7x's. So from 0x's to 7x's, so I have only 8 summons. So there are many, many simplifications happening here. Do you agree? 2 to the 7th is much bigger than 8. Good?
Okay.
Okay, I hope you see that, guys. All right, so I just group them by how many x's I have. If I have 0 x's, or if I have 1x, or 2 x's, or all the way to 7th x's. So it's from 0 to 7, it's 8.
8. Right.
Exactly. Good. Okay. And there is a question. Okay, thank you, Andre. And I hope all of you are with me, or if not, guys, not to despair just yet. You can stay after class and we can discuss that. Now, where Sarah, where you said whatever number you mentioned, you see, when I simplify, some terms appear only once. Let's, for example, the addition of the term x to the power of n in general will appear once because there is only one way to create x to the n. Each parenthesis had to contribute an x. Do you see that? Each parenthesis had to contribute an x. Whereas terms of the form x times y to the n minus 1, remind me please, how many terms do we have? X times y to the n minus 1, how many terms do we have? N choose 1, Carmen. Yes. Do you understand why it's n choose 1? What are we choosing? What is the n? N is the number of available parentheses, and 1 is the one parenthesis which will be assigned x. Agreed? Because what happens in this experiment, the parenthesis is assigned either the value x or the value y. Yes? Now, in general, if you look at x to the k, y to the n minus k, how many copies of x to the k, y to the n minus k do you expect to have? Simple question, I hope. N choose k. Precisely, it is n choose k. Do you and why is that n choose k? Because look at it, guys. It's n choose k because we need to assign to k of the parentheses the value x, and the remaining parentheses will be assigned the value y. So when we say n choose k, we are choosing which exact k parentheses will display the x. Good? So let's move on. So that gives us the binomial theorem, very important theorem, very useful. X plus y to the n in sigma notation is equal to sigma from k0 to n choose k, x to the k, y to the n minus k. What this means, what the sigma notation means, in case you don't remember, it means that I start with 0. So this means start with 0. So it's n choose 0, x to the 0, y to the n. Okay? It's x to the 0, y to the n, plus n choose 1, x to the 1, y to the n minus 1. The powers always add up to n, all the way to n choose n, x to the n, y to the n minus n. Okay? So, for instance, here is a comprehension check. What is the coefficient next to x squared, y squared? I think we already did a few comprehension checks. So what you can imagine is here are the parentheses. Parentheses 1, 2, 3, and 4. Just to try to illustrate to you what happens, guys. You see? Here I try to illustrate with colors and what happens here, right? So if I have x squared, that means 2 of the 4 parentheses were assigned the value x. So here are the possibilities, you see? Look at it, guys. Trace where the x's are located. There are exactly 6 possibilities, which I can do without listing them out. In this case, it's simple enough. I actually bothered listing it out. But the idea is so that you see where the n choose k comes from, you see? For instance, the first choice means the first and second parentheses contributed the x. In this case, the last 2 parentheses contributed the x. In this case, the second and the fourth parentheses were the contributors of x. So when you add them up, you get the coefficient. You understand? The coefficient is added as many times as it's possible to come up with contributors. And without listing it, you can see it's 4 choose 2. And 4 choose 2 is 4 factorial over 2 factorial, 2 factorial, which is 3 factorial, which equals to 6. Here is a comprehension check that is slightly more difficult. Okay, guys? Could you please tell me what is the summation h choose 0 plus h choose 1 plus h choose 2 all the way to plus 8 choose 8? What is that equal to? And we will solve it in 2 ways. We have to learn to solve it through a story. Okay, Andre? So I give you guys 2 more minutes to think about it, then we move on. Okay, that's good. Yofi, good. Okay, Ben. We will solve it, I believe, in 2 ways. Okay, Erin, good. Good. All right, guys, I think a few of you are getting the hang of it. So let's get on with it. So here is one observation. Look at it. So what are we expanding? Those are the coefficients when we expand x plus y to the power of 8. Yes? All we have to do is let x and y be equal to 1. Look at it. You see this? 8 choose k, 1 to the power of k times 1 to the 8 minus k. What is that expansion of? That's the expansion of the instance where x is 1 and y also equals to 1. So it's 1 plus 1 to the power of 8, which simply is 2 to the 8. So that's a perfectly nice way to solve this question. I hope you all see that. Yes, guys? You all see that this is just, what I see is that, oh, the coefficients look like they are h choose 0, h choose 1, h choose 2. They are the coefficients of 8 choose k, which is the coefficients of the expansion to the power of 8. Good? All I'm missing is the x and y. But I can get, if x is equal to 1 and y is equal to 1, then we have 1 to the k times 1 to the power of 8 minus k. That's my x, that's my y. That looks perfectly like the summation for the binomial theorem. Yes, guys? So if you don't remember this sigma notation, I mean, if you took calculus, you should. But what I'm saying is then what you have here. Here you have x to the power, or 1. Let's just go with 1. 1 to the power of 0, 1 to the power of 8. This is 1 to the power of 1 times 1 to the power of 7. This is 1 to the power of 2, 1 to the power of 6. And this is, of course, 1 to the power of 0 times 1 to the power of 8. Okay? That's really what this succinct notation is supposed to be showing. Now, let's do it yet another way to see combinatorial properties. This is called a story proof. Okay, guys? So another thing to imagine is to try to see what exactly is somebody counting here. Okay? What exactly could be counted? So suppose that I have 8 students. And I list those students as student 1 through student 8. And this is my protocol for attendance, which, by the way, will be soon applying if you don't come to class. And the protocol for attendance means student 1 either did not come or came, 0 or 1. 0 or 1 for each of them I can assign, right? So then 8 choose 0 means what? It means that no students came. Okay, if 8 choose 0 means that I did not choose any students that were assigned the value 1. 8 choose 1 means I chose one of the 8 students to assign the value 1. It means the set of attendance rosters where one student came and nobody else decided to show up. Do you agree? So, and then 8 choose 2 means two students came. What are the possibilities of assigning 2 students? 8 choose 2 students, assigning them the value 1 and everybody else the value 0. Okay, so in this sense, we have that that 8 choose 0 plus 8 choose 1 all the way to 8 choose 8 represents the possible attendance rosters between nobody coming and everyone coming. And instead of doing it by how many students came, I can just imagine doing the basic principle of counting. First student either came or not, it's 2 possibilities. Next is 2 possibilities, 2 possibilities. So altogether 2 to the 8 possibilities, you see? Because those both procedures are counting the same thing, I know the formulas must be equal. You understand? I just recognize that one procedure and the other procedure, they count the same thing, so they produce equal formulas, equivalent formulas. Okay, here is another example of a useful identity that if you understand what is being counted, you can easily come up with the numbers. So here is the useful identity, guys. N choose R is equal to n minus 1 choose R minus 1 plus n minus 1 choose R. Okay? So if you try to verify it using algebra, first of all, you don't understand where it's coming from. Secondly, it's very tedious. So here is what we do. So suppose that I have n individuals in my classroom, and one individual, let's see where this individual is, his name is Jimmy. Jimmy is very special. It's a special boy. So I label Jimmy with the letter N, right? The last person, N is Jimmy. And the numbers 1 through n minus 1 refer to everyone else. Good? So then imagine that what we're going to do, I'm going to pick our students to interrogation, to personal grueling interrogation, as they do, to make sure that they understand the information and they're not just hiding behind a mask. Okay, so here is my Kafka protocol for the people that were chosen to be interrogated. In this case, I filled it in order as person 1, person 3, person 4, all the way to person R plus 1. Good? If you are not comfortable with this, I can give you later numbers. I'm just doing it abstractly first, and if you want numbers, I will do numbers in a moment, okay? So then I can, once I printed all possible choices of our individuals, I can list my documents into 2 piles. I can have one pile containing documents where Jimmy is absent, and another pile containing documents where Jimmy is present. You understand? So I print all possible documents, and on the document, our students will be listed. Which of those students that are listed will be going through interrogation. Understood? So here is pile 1, that's where Jimmy was picked, and pile 2 where Jimmy is not picked. So the pile where Jimmy was picked ends in the number, it ends in the number n, because Jimmy is the last number, right? And I have to write it in order. So the pile where Jimmy was picked, the document ends with the number n, and it has additional r-1 spaces to be filled in. Good? The pile where Jimmy is absent has r spaces to be filled in, but one of those spaces cannot be n. So how many possibilities to fill in this document? It's n-1, choose r-1 possibilities, right? n-1 for the number of candidates available, and r-1 for the number of spaces available. Whereas if Jimmy is absent, I have n-1 candidates available, and I have to fill in r spots. So altogether, I have this, that n choose r equal to n-1 choose r-1, sorry, plus n-1 choose r. Let me just, to reiterate, I will do that with numbers. Okay, guys, this is the procedure. Imagine that I have 4 students. 4 students, and one of them is Jimmy. So the students are labeled 1, 2, 3, 4. Good? And who is the 4th student? That is Jimmy. Good? 4 students, the 4th is Jimmy. I am going to conduct interrogation of 2 students, right? So if you understand how the Stasi was working, right? That's exactly very good to think about. How did the Stasi work? The Stasi would have a document, and this document would look like this. In this case, this is my document. Right here, I have to put the smallest and then largest number of the people interrogated. So how many ways to fill in this document, guys? Where I cannot just write, let's say 3 followed by 1. If person number 1 and person number 3 were selected, I have to write 1 and 3. Yes? How many possible ways of filling this document are available to me? Help me, please, fast. $12? No, not 12. We have only 4 individuals. Slightly less. 4 choose 2, exactly. 12 so yes, sorry. So Sarah, you listed all the ways. You're allowed 3 and 1, but 3 and 1 is the same as 1 and 3. Okay, 4 choose 2. There are 6 possibilities. 4 choose 2 or 6 possibilities, okay? Now this is, and now I have, in other words, I have 6 documents. If I print every possible combination of 2 people, I will have 6 documents exactly, you understand? Now let's sort those documents. Help me sort those documents, guys, right? So here is documents, number of docs with Jimmy. Number of docs with Jimmy. It means that what can you tell me about if I stack those documents and you look at them, what do you see here? What do you see in the last box? Clearly, in the last box, you see the number 4 because Jimmy is present. Yes, the number 4, whereas this is not known, right? I mean, this you just right away know that if it's if documents with Jimmy are in this pile, how many documents with Jimmy are in this pile? Help me, tell me how many documents are there here. How many ways to fill in this number, this remaining number that will make a document? 3, precisely, right? So this number is either 1, 2, or 3. So it's 3 documents, or 3 choose 1, which is the same as 3. Yes? That's documents with Jimmy. So it's 3 documents. Now, how many documents without Jimmy? So then you see this document box, and you do not know right away without looking what's this number and what's this number, but you know that none of those numbers are 4. Exactly, right? So we don't have 4 as a candidate, so it's 3 choose 2. Which also happens to be 3. 3 choose 2 is also 3. You can easily establish that. So that means that we have that 4 choose 2 must equal to 3 choose 1 plus 3 choose 2, or 3 plus 3, which is 6. That's a very useful procedure for actually calculating with reduced complexity combinations. You understand? You can create a recursive formula, and that's in fact what we're going to do in a moment. That's the triangle. That's the Pascal's triangle, as you might be familiar with. How does 3 choose 2 equal to 3? Well, you can of course calculate, but you can also do the following. You see 3 choose 2. Look at it. You have 3 individuals. Let me just erase this. 3 individuals. 1, 2, 3. Now, if you have to choose 3 of them, the symmetric thing to tell me is which individual was not chosen. You agree? If I choose 3 individuals, that means 1 individual wasn't chosen. So either it's individual 1 who was not chosen, or individual 2 who was not chosen, or individual 3 that was not chosen. Therefore, 3 choose 2 equals to, what did I say? Did I say 6? I should have said, I don't remember. Did I say 6 or did I say, I said 3, right? I'm not insane. Or am I insane? Let me see. Yes, I said 3. I mean, don't scare me. Right? So I said 3. So it's either this or that or that. So 3 choose 2 equals to 3. You see, when I say either 1 or 2 or 3, I mean the individual that was not chosen. And that tells me right away who was chosen. Good? I don't, so who forgot our factorial? I mean, 3 factorial, well, I mean, what Andre, what you wrote on top, it's 3 factorial over 3 minus 2 factorial, and 2 factorial, which will be 3, right? Because you divide by, you divide 6 by 2. Good? So I hope you're with me, guys. Let's move on. So that's the general formula, and notice the strategy I used to justify it. I didn't do any calculations. I just realized that the right and left, they count exactly the same thing, right? The 2 parts of the equation are just formulas that are different methods of counting the same thing. When I visualize it, I know the answer instantly. At least I know that they're equal instantly. Pascal's triangle is built on that very principle, on the Jimmy principle. Okay, guys? So here is what you do. You write 1, 1, and 1. You write this triangle 1, 1, and 1. And then on the next layer, look at it. You see this, guys? The 1 and 1, you add them and you get 2 in the middle. And then you write 1 at the edge, 2 and 1. And that will correspond to the coefficients expanding x plus y squared. Next, what you do is, guys, look at it. You add width. You add 1 here and 1 here. And then what you do is this. Look at it. 1 plus 2 is 3. 1 plus 2 is 3. 2 plus 1 is 3. You see how you go? You just sum the immediate two numbers on top of what you have here. Okay, and so here we have 1, then we have 1 plus 3 is 4, then we have 3 plus 3 is 6, then we have 3 plus 1 is 4, and you write 1 here. Let's see if you understand it. Help me. You can actually write it the full row. What would be the next layer, guys? Write the next layer for me, please. If you understood this pattern, tell me what's the next layer. Okay, so let's, so you see it, so we begin with 1. 1 plus 4, I write it between them 5. 4 plus 6, I write 10. 6 plus 4, I write 10. 4 plus 1, I write 5, and 1. Thank you so much. Good. So you understand how this triangle is built. And what is this triangle? It's an algorithm for recursively calculating combinations. So you can very quickly calculate combinations by just going through the layers of the triangle. Next layer will be next combination. Yes? So what is, for example, if you look at this 10, guys, what does this 10 represent? This 10 is what? This is, look at it, this is the expansion x plus y to the power of 5, right? So this 10 represents 5, choose 2. Okay, look at it, this is 5, choose 0. This is 5, choose 1. This is 5, choose 2. You understand? So those layers of the triangle, if you don't have a calculator, but you can go down the layers, you can very quickly calculate combinations. Okay, if you want to calculate 6, choose 5, for example, or 6, choose 2, or 6, choose 3, you just have to go to the 6th layer. If you want to calculate 6, choose number, go to the 6th layer. 7, choose some number, go to the 7th layer. Now, it works based on the Jimmy principle, guys. Why does it work? Look at it. The top layer is, look at it, this layer. Let's look at this layer here. This is 2, choose 1. And this here is 2, choose 0, I'm sorry. This is 2, choose 1. And this is, let me just write it differently. 1 second, it's not nice. Here. So we have this layer, guys. All right. So what is this? This represents 2, choose 0. This represents 2, choose 1. And this represents 2, choose 2. Okay. Now, if that's what they represent, look at it. If I add those terms together, if I add 2, choose 0 and 2, choose 1, what am I going to get? I'm going to get 3, choose 2. 3, choose 1, my apologies. It will be 3, choose 1. 3, choose 1. Because remember what you do here, guys. If you have n minus 1, choose r minus 1, plus n minus 1, choose r, okay? All you have to look at in this summation will give you n choose r. And what is the n? Look at it. So what you see is you select, this is for the previous layer, so just add 1 to it. And look at this box to tell you what's the lower index, right? So I look at this box to tell me that this is 1. And I look here to tell me that the top number is 3. You see that? So the Pascal Triangle is a very, very efficient way to calculate combinations when you don't have a calculator, or just if you want to understand how that works. If you want to quickly expand high powers, that is very, very efficient technique. So here is an instance how I can expand it very quickly. Look at it. I want to write x plus y to the power of 4. So I right away know that it will be x to the 4 times 1, 4 times x cubed y, plus 6x squared y squared, plus 4xy cubed, plus 1 y to the 4th. All I do to get those coefficients is that I read this last line here. 1, 4, 6, 4, 1. So you see 1, I begin with the highest power of x, then the next number, x is reduced by one number, and y gains a power. 6x squared y squared plus 4xy cubed plus 1 y to the 4th. Now, here, guys, I will show you this line. You see this line? Please tell me, since you understand it, please expand and write in the notes what the answer is. What is x plus y to the power of 5, right? And tell me what it is. Well, I want the full expansion of x plus y to the power of 5. It's a bit annoying to type it, I presume, right? All right, so I'm going to write it. I'm hoping that I am not skipping anything that you don't understand. So look at it. This would be 1 multiplied by x to the power of 5 plus 5 multiplied by x to the 4y. Yes, exactly, right? Plus 10 x to the 3y squared. Yeah? Okay, good. And then plus 5 x 2y cubed plus I missed a 10, right? It should be a 10 here. Plus 5x y to the 4 plus y, or 1 times y to the power of 5. Good? Yeah, hopefully it's correct, guys. Yes, it's easy. Just making sure. Right, if you can use Pascal's triangle, then you don't have to torture yourself with a lot of algebra.
Arkady?
Yeah.
Can you go back to the answer for the x plus y to the 5th?
Okay.
Please.
Yeah.
Thank you. Yeah.
Okay, good.
All right. Thank you.
Sure. All right, guys. So now let's do a comprehension check. See if now this is a more interesting question, right? This is just the expansion. We did a question like that. Now, please help me with this situation, guys. Use a combinatorial argument. In other words, tell me a story. I don't want any algebra. Tell me a story about what this summation equals to. Maybe just instead of a lot of additions, what is that equal to? You see, we have n choose r times m choose 0 plus n choose r minus 1, m choose 1, all the way until I have n choose 0, m choose r. Okay, this is the summation written in compact sigma notation. You see, what is the sum equal to by a combinatorial argument, by a story, just like I did a Jimmy story. Give me a Jimmy story. All right, guys. Imagine that this is 1001 nights, Arabian Nights. So if you don't think of the story fast, you know. That's amazing, Melissa. Very, very good. Okay, so we already have a story. So entry-level workers and managers, that's one story, right? So just to make it just for somebody who has no idea what people do in offices and avoided offices for as long as it could exist and still tries to avoid them, I will give this example. Okay, so very simply, in a class, we have n girls and m boys. Good. So if I will summon k of those students to speak with the director, then how many possibilities are there to choose the people? I mean, I can choose simply n plus m choose r. You agree? N plus m choose r means that out of both boys and girls, I choose r individuals to, you know, select them and send them somewhere. Yes? Now, I can break that selection based on the possibilities of choosing from one category or from another category. Okay? So what you have is I could have chosen only girls and no boys. I could have chosen all but one boy. Everyone is a girl except for one boy, all the way to just choosing boys. Good. So you understand that if I print those documents, I can arrange the document by documents that contain exactly R girls, documents that contain exactly R-1 girls, all the way to documents that contain only boys. Yes, and there will be several piles, many piles. Yes, altogether 0 through R, so R plus 1 piles. If I choose 5 individuals, there would be 6 piles. Do you agree? 0 boys, 1 boy, all the way to 5 boys. Good. So 6 piles. And that finishes this lecture. The next, let's hope we can do it very fast, is a generalization of that idea, multinomial coefficients. Okay, so this is the story. So combinations are a sort of way to assign destiny, right? And I think right away of Akujava is a great poet, and he says, "Прощай, Москва, душа твоя всегда пребудет с нами." Basically, people are waiting to receive the rifles and to be sent to their destinies. And this is really then a similar example. So 3 dragons have each kidnapped a princess. 10 brave knights are sent to rescue them. 3 to the first princess or against the first dragon, 3 to the second princess, and 4 to the last princess. Now, if all those knights have been eaten by the dragons, how many destinies are possible, right? It's a sort of, what do you call it, grab hub for dragons, right? So this dragon number 1, wants 3 knights for breakfast. Dragon number 2 wants 3 knights for breakfast. This dragon has an eating disorder. He wants 4 knights for breakfast. Okay, so how many ways to ship the knights among the dragons? Okay, so of course we can label the knights. The knights are distinguishable, so we label the knights as knight 1, 2, 3, all the way to knight number 10. Good. And if you have been to cafeteria, you know, we can color code, right? So we have a tray containing 3 knights for dragon number 1, tray containing 3 knights for dragon number 2, and tray containing 4 knights for dragon number 3. Good. You understand? We are assigning the trays. Okay. Now, obviously, look at it. The knights that were placed on tray 1, they can jump around and they can, you know, decide how they stand in line. It doesn't matter. As long as they do not jump over into another tray, it does not change their destiny. They're like shipped in one package. Same thing with other knights. So altogether, if you arrange them in order, look at it. If I fill the numbers in order, there are 10 factorial possibilities, right? But 3 factorial rearrangements of tray 1, 3 factorial rearrangements of tray 2, and 4 factorial rearrangements of tray 4. So the codes that we create have redundancies, have synonyms. Good. So we take 10 factorial, which is the number of documents, divided by number of synonyms, and that gives us number of destinies. Is this clear? Yes, clear, completely clear, guys. You imagine how the order is being selected, yes? Do you? Well, I hope so. I mean, I can explain more, but I don't want to over-explain if I don't need to. So the general situation is we have R dragons and N knights, and dragon number 1 will eat N1 knights. Dragon number 2 will eat N2 knights. Dragon number 3 and 3 knights, all the way to dragon number R eating NR knights, where the sum of the knights is N. Everyone will be eaten. Good. So the multinomial coefficient, as this one is called, is N. Choose N1 and 2 all the way to NR, and that's defined as the total number N factorial divided by N1 factorial and 2 factorial all the way to N sub R factorial. The numerator indicates the number of ways to put the knights in a row. But if they are put in a row, they are standing on top of trays. Okay, so the N factorial is not the destiny. And what you have on the bottom, that represents the knights jumping around between each other, right? But not switching trays. Good. So if the knights kind of interchange, if the knights on one tray interchange their places, this tray is still going to the same dragon. Good. But so that means that's why we divide. Is that good? And so let's see how. Look, guys, how do we expand? Let's now understand how to expand this form. We don't add just 2 terms, we add in general m terms, x1, x2, all the way to xm to the power of n. Good? we can use the same idea. We can say that there is 1 parenthesis, 2 parentheses, all the way to the n parentheses, right? To produce to the power of n, we have n parentheses. Good. Now, each parenthesis contributes exactly 1 term. So we have n boxes. How many possibilities are there for box number 1? Could you tell me how many possibilities to write something in box number 1? Remember, before we had 2 to the power of n. How much do we have now? So how many possibilities for box number 1, for box number 2, and onwards? Well, in this case, Andre, be careful, look at it. We're dealing with expansion here. We have x1 plus x2 all the way to xm, okay? Let me see, if it's not so obvious immediately, let me then give you a concrete example. So suppose we have x plus y plus z raised to the power of 5, okay? Good, we have x plus y plus z raised to the power of 5. So if I were to expand it, right, I will have a summation of a lot of terms. So definitely whenever I multiply the parentheses, right, you have x plus y plus z. That's first parenthesis, x plus y plus z, that's second parenthesis, all the way to x plus y plus z, fifth parenthesis, yes? So how many possible contributions can there be for parenthesis 1? Right, parentheses, we have parenthesis 1, parenthesis 2, parenthesis 3, all the way to parenthesis 5, right? If we expand it, what you will see is a term from parenthesis 1 multiplied by a term from parenthesis 2 multiplied by a term from parenthesis 3 all the way to parenthesis 5. How many possibilities for terms in parenthesis 1? Sorry, yes, how many? That's right, how many terms? How many possibilities? No, much easier than that. Guys, do you understand how multiplication works? Well, 0 or 1, that's only, look at it. Be careful, guys. Do you see how multiplication works? It's a bit annoying to write it all out. Exactly. Somebody finally said it right. So Colin and Jennifer, the answer is indeed 3. What happens when you expand, guys? Look at it. When you expand, this parenthesis will either contribute x or y or z. The next parenthesis, independently of what the first did, will contribute either x or y or z. You understand? And we sum over all possibilities. Okay? Okay, maybe if this is not obvious to you, perhaps let's do x plus y plus z squared. Okay, so that is x plus y plus z multiplied by x plus y plus z. You really make me work here, guys. So that is first parenthesis, this is second parenthesis. What can we have here, guys? Well, we can have, look at it. If I expand it, it's x times x, right? So I can have x times x. So that means that first and second parenthesis contributed an x, plus first parenthesis contributed an x and the second a y, plus the first contributed an x and the second a z, okay? Plus we have the same exact situation where the first parenthesis contributed a y, and plus where the first parenthesis contributed a z. Okay, so we have 3 plus 3 plus 3 possibilities. Do you see that? So how many possibilities for the first parenthesis? 3. For the second parenthesis, 3. So in general, in this case, you have 3 to the power of 5 summons in this case. Okay. Some of them, of course, can be simplified. Good? Are you with me, guys? Do you see what I'm doing? Or are you confused? It looks like a few faces are desperate.
I'm just confused about what you mean by possibilities.
Well, in this case, when you expand, look at it. When you multiply one parenthesis times another, each parenthesis contributes exactly one term. So between additions, each parenthesis contributed one term. Do you see that? That follows from distributive law, right? So when I distribute the parentheses, you know, I can have with square. It's obvious, right? So when I have the square parenthesis, look at it. I have x multiplied by x plus y plus z, y multiplied by x plus y plus z. So you see what happened here. So when you finish expanding it, each parenthesis contributed either an x or a y or a z, independently of what the next parenthesis did. If you have many more terms, it will still work the same way. Each parenthesis, you consider all possible combinations of a contribution from first, second, third parenthesis. If you have 100 of them, it's the same. All possible contributions from first, second, all the way to 100th parenthesis. Before I simplify it, I have, in this case, that's what I'm trying to say. If I have x plus y plus z to the 5th power, before I simplify anything, I have 3 to the power of 5 summands. Is it clear? Because each box, each box records the contribution from a particular parenthesis. For false box, records the contribution from first parenthesis. So there are 3 possibilities, either x or y or z. Second box independently, either x, y, or z. So there are 3 possibilities. The next one has 3 possibilities. The next has 3 possibilities. So 3 to the 5 possibilities for the summation. What we had before is 2 to the 5, right? If it's x plus y to the power of 5, it will be 2 to the 5. What's the 2? The 2 is the number of variables. In this case, it's 3. It's the number of variables. Good? Good. I hope you understand, guys, right? Not just agree with me, but understand. You actually see it. So this is the situation in general. If I have m variables, right? 1, 2, all the way to m. First parenthesis, and it's to the power of n. That means I have m variables contained within each of the n parentheses. The first parenthesis contributes how many terms? So how many summands if I expand this expression without simplifying? How many terms do I add? So m multiplied by n, so n to the power of m. Jennifer, you're absolutely right. It's m to the power of n. Do you see that? Why m to the power of n? Because this has m possibilities by the general principle of counting. It's m multiplied by m multiplied by m n times. So it's m to the power of n. Yes? Boland, I hope you didn't lose consciousness there. Good? Understood, guys, where we have m to the n. Now, let's try to simplify it. n1 plus n2 all the way plus n sub m is equal to n, right? So I can group, right? Look, this is part of my, let's see, my next problem, guys, right? Is that if I can group, if let's say this is how many copies I have of x1, this is how many copies I have of x2. If I look at this type of term, right, it's a bit harder to actually arrange it very well because you have a lot of different things happening, right? You cannot just group it by, when you have 2 of them, you can just see how many x you have, and then you know how many y you have. But here you have to kind of consider all possibilities where the number of x1s and the number of x2s and the number of n sub m's, they add up to n. Okay, so if I have one such term, then the coefficient next to it will be what? The coefficient next to it will be, so the coefficient next to, let's say, let me just give you a concrete example. Maybe it will be easier for you. If I had x plus y plus z to the power of 5, okay? And let's say clearly there will be this type of coefficient, guys. So x to the power of 3, y, z. Do you agree that 3, y to the 1, z to the 1 adds up to 5? Yes? What is the coefficient next to this term? In other words, how many terms in the summation will I see x cubed, y1, z1?
5.
You don't need to give me the number. You can give me a sort of way to calculate it. Just give me the formula for it, in other words, the coefficient. All right, guys, let me give you a hint, okay? Who are the dragons in this problem and who are the knights? It's exactly the same situation. There are dragons and knights here. Who are the dragons and who are the knights? No, total is just, well, who is the dragon here? So how many dragons do we have here? And how many knights? And who are the dragons and who are the knights? What does x cubed mean? X to the power 3 means that 3 of what became x? Exactly, Jennifer. X, Y, Z are the dragons, precisely. And who are the knights? Not just how many, but who are the knights in this problem? The dragons are the variables X, Y, and Z, and who are the knights? Well, Jennifer, 311, it's kind of not specific. The knights are not 311. You mean maybe 911 if you want to call help. R is just a number. R, those are pirates. Who are the knights here? No. Mayamiko, you're calculating. You're giving a number. The knight is an object, right? I mean, so the knights are there are 5 knights. Exactly. There are 5 knights. By the way, I should show you a good song by Esther Farim. It's specifically about 3 knights. You see, that's how it inspired. It's a lullaby for a kid that the lullaby was so good that the kid later might have committed suicide. It's an amazing lullaby. Deeply beautiful, deeply serene and scary at the same time. If you want to listen to it, I will play it to you. It's in Hebrew. I can give you a rough translation. Okay, so the answer is this, guys. Look at it. The parentheses. You see, we have parenthesis 1, parenthesis 2, all the way to parenthesis number 5. And those parentheses will go to either X or Y or Z. So what is this representing? This represents the situation where dragon X received 3 parentheses, dragon Y received 1 parenthesis, and dragon Z received 1 parenthesis. Do you understand? The parentheses are becoming X, Y, or Z, or becoming dinner for X, Y, and Z. It's up to you how you think of it, right? So the answer here is 5 knights that you put on the tray, 3 of those knights are assigned destiny X, 1 is assigned destiny Y, and 1 is assigned destiny Z. So the answer is 5 factorial divided by 3 factorial, 1 factorial, 1 factorial. Okay, that's counting how many possibilities here. But what are the knights? The knights are the parentheses. What are the dragons? They are the X, Y, and Z. Same exact situation if you realize that we can do it this way. Yes? So 5 choose 3. Well, 5 choose 3 is not 20. 5 choose 3 is, well, you're right. Sorry, it's 5 choose 3, it's 20. You're absolutely right. It's not choose, it's just there is a 1 factorial and 1 factorial. So it's 20, yes. Good? So in general, the situation is as follows. So it's n choose n1, n2, and m represents that n1 of the knights. That the n is the parenthesis, and one of the parentheses we're attributing or producing x1 to the n to the power of 1, right? So it's so n1 we're producing. There were n1 copies of x1. There are n2 copies of x2. There are n sub m copies of xm. Okay. So that's how many of the parentheses were delegated the destiny of becoming either x1, x2, or xm. And you cannot write a multinomial summation as nicely as you can for binomial. You see, so because this is just kind of rather complicated. You see, the summation is over all vectors where the sum of the coordinates is n, because those represent different, nutritional, well, different dietary plans for the dragons. For the X, right? So any one such thing is a different dietary plant. How many knights is a particular dragon getting? So here is a question, guys. Let's see if you can solve it. 9 pupils are divided into 3 teams, each consisting of 3 players. Okay. If one team will wear a red shirt, another blue, and last green, how many outcomes are possible? You understand? So we have 9 pupils are to be divided into 3 teams consisting of 3 players each. There will be a red team, a blue team, and a green team. How many outcomes are possible? Okay, Andre, you are right. But so what happens here, guys? Why is that the situation? You see, we have the knights here in this case are the pupils, and the dragons are the jerseys, right? Are the teams. So there are 3 teams, and each of them takes 3. Okay, so the answer is, and here is we do it by Kafka protocol, guys. You see, so this is the number of players. You will see it for the next problem, right? This is the number of players listed in order from smallest to largest that are assigned the red jersey. In the middle, from smallest to largest, are are pupils assigned blue jersey and the green jersey. So for instance, imagine that we labeled the 9 individuals 1 through 9, and 2, 5, and 3 are assigned red, 9, 1, 4 are assigned blue, 7, 8, 6 are assigned green. The input code is 2, 3, 5, you have to put it in order, 2, 3, 5, 1, 4, 9, 6, 7, 8. You understand? So this, I colored it so it's easier for you to read, but if I know this code in this order, I know exactly who was assigned what. So in these boxes, they have to be put in order. And to count it is 9 choose 3, 3, 3, or 9 factorial over 3 factorial cubed. Good? Bear with me just one moment. Let's finish B. Only red shirts arrived. 3 players will be assigned red jersey, and the remaining teams will not be wearing distinguishing colors. You understand? So there is only red jerseys that we can dress, and the rest we don't distinguish. We don't know. Who is red, who is green? They did not receive the assignment. All right. It's important to think of the document, guys. Right. So it's not, even if you can solve this one without a document, I want you to have a very, very clear visual. Yes, exactly, Sarah. We're assuming that 6 are no color. They are still divided into teams of 3, but we don't know who is green and who is red. Sorry, who is blue. We know the reds, but we don't know green or blue. Thelma, what is this? Did the cat step on your keyboard, Threna? All right. So let's see how we do it together. Here is the situation in A. That was the protocol. Now look at it. Now, blue and green are interchangeable. You agree? So there are some codes. Look at it here. I keep the red and I erase distinction between blue and green. So I can interchange the codes. Do you see that? So 6, 7, 8 in the middle and 6, 7, 8 in the last place means the same thing, because I cannot distinguish green and blue. So I erase those things, right? So what happens is this, guys. What happens if you interchange those codes? It means that if the previous document counted 9, choose 3, 3, 3 documents, the new one is counting exactly half, because I can make interchanges of those boxes, right? So we now have 2 synonyms. So it's the previous number divided by 2. Do you see that? Because I can now interchange green and blue. And that means I have synonyms, further synonyms for this process. Last question, promise. What happens, that's a comprehension check, right? And then we finished with this lecture. What happens if no shirts arrived? So we still have teams 3 and 3 and 3, but no shirts arrived. What's the number of possibilities of assigning the teams?
Isn't it 0?
No, because we have 3, 3, and 3. We can still group people into groups of 3. It's not 0. We can still assign people into teams without dressing them in jerseys, without making them.
Oh, no. Oh, never mind. All right.
So Anton says 1/3. Anton, be careful. Maybe not 1/3, but something similar. Andre, you are absolutely right. Look what happens here, guys. So now, in the last example, it's 1/3 factorial times the previous answer. Because look at it, 9 choose 3, 3, 3 worked. That's why I think of protocols. You see, worked when I had the full protocol, when it was like this. Okay. Now, if I erase red, blue, and green, it means that I can interchange the red, blue, and green boxes and place them in any order I like. So I have 3 factorial redundancies, which means I divide by 3 factorial. You follow that, guys? So I think very, very, I document my thinking. I imagine a document, I imagine how I feel in the information, and I imagine what happens if the document no longer describes the situation uniquely. Okay, I mean, if I write the numbers as before, it still works. It still divides the team, but it actually doesn't show me a distinguishable outcome, because the fact that I rolled it to be red team, they're not red. I don't see them to be red. Good. So to summarize, Multinomial coefficients means assign distinguishable individuals among distinguishable destinies. You understand? So let's say the destiny here, the distinguishable destiny here is red, blue, or green. You become red, or you become blue, or you become green. The distinguishing entities that you assign are the pupils. Good? So I can count in this situation, and then when I do not distinguish the destinies, or some of them, I can just staple together documents that describe the same thing. All right, guys. So we call it a day. We are not going to continue with the next lesson today, but if you want to watch one question of what, when, where, or if you have questions after class, you definitely have to watch what, when, where, at least one question, right? And of course, if you have office hours problems, then we can discuss the material further. All right, I stopped the recording. Goodbye if you cannot wait.